Welcome back to part 2 of our introduction to eigenvalues and eigenvectors. So again, we see that if ax is equal to lambda x, where lambda is a scalar, we can do a little bit of arithmetic to find out that a minus lambda I all times x equals the 0 vector. So we want to find out the special non-zero x vectors and the special constants that go with those that will make this true, so that matrix multiplication is simply a scalar multiplication. So let's take a look at our matrix and let's find his characteristic equation by finding a minus lambda I and then doing the determinant of that and setting it equal to 0. So if we do a minus lambda I, that's going to be 1, 2, 3, negative 4 minus lambda 0, 0, lambda. So we will get the matrix. Let me do an equal sign here. 1 minus lambda, 2, 3, and negative 4 minus lambda. So if we take the determinant of this guy, who's a 2 by 2 matrix, so he's pretty easy, and set him equal to 0, we're going to get 1 minus lambda times negative 4 minus lambda minus 2 times 3, or 6, and set that equal to 0. Let's see what happens. So let's distribute through here. So negative 4 minus lambda plus 4 lambda and plus lambda squared minus 6 equals 0. So if we take this guy, so lambda squared, we've got a minus a lambda and a plus 4 lambda, so that's plus 3 lambda, and a minus 4 and a minus 6 makes minus 10 equals 0. So this guy is our characteristic equation. Now technically, here is also the characteristic equation, but usually we like to see him either in his standard form or possibly even in his factored form, which is where we're headed next. So let's take this guy and see if he'll factor. So we've got lambda and lambda. Factors of 10 are 10 and 1. That's not going to work. Ooh, but what about 5 and 2? And if I make a positive 5 and a negative 2, that will work. Okay, so we then know that our characteristic equation will lead us to the values of lambda equals negative 5 and lambda equals 2. Oh, that's interesting. Those happen to be the numbers that we got up here, those scalar multiples. So now that we've got our eigenvalues, we're going to plug them back into the matrix, or well, into this a minus lambda ix equals 0, and find out what the special eigenvector is for each one of those guys. So I made my font a little bit bigger, so I'm going to have to go to the next page. So we had an eigenvalue of, let's start with the negative 5. Okay, so if we plug that back into our a minus lambda I times x equals 0 system, let me move that over and up so you can see what's going on. We're going to have, going back to a minus lambda I, so I'll stick a negative 5 in here and a negative 5 in here, but this is a linear system because he has an equal 0. So 1 minus a negative 5 is 6, 2 is 2, 3 is 3, and negative 4 minus a negative 5 is a positive 1. And since this is an equals, we're trying to solve for what x1 and x2 are going to be to make this true. And if we RREF this matrix, we will end up with 1, 1/3, 0, 0, 0, 0, which tells me I'm going to need a parameter, which is good. And we'll talk about why later on in the course. So x2 would be, I could call it t, but I'm actually going to be tricky and call him 3t, because then that makes this guy be, instead of 1/3 of a t, it'll be 1/3 of negative 1/3 of 3t, which is simply a negative t, which I could write as t times negative 1, 3. Okay. What about the other guy? So what about lambda equals 2? Again, if we plug that into the a minus lambda I times x equals 0 vector system, we're going to get 1 minus 2 is negative 1, 2, 3, and negative 4 minus 2 is negative 6. So this system, so here's the a minus lambda I, here's this guy, and we're solving for x. Again, if we RREF, we will get 1, negative 2, 0, 0, 0, 0. And you will always get at least one row of zeros at the bottom of your matrix when you do this, for a reason that we'll talk about later on. So once again, we would find out that x sub 2 is going to need to be a parameter, so I'll call him t, and x sub 1 then would be 2t. So if I factor out the t here, I get the vector 2, 1, and since t is just a scalar multiple, we want to write these in their eigenvalue, eigenvector pairs. So when lambda equals negative 5, that works, but it only works on scalar multiples of the vector negative 1, 3. Okay. And lambda equals 2 also works, but he only works on scalar multiples of the vector 2, 1. So let's go back in and look. Hey, check that out. So we can see that negative 1, 3, his scalar multiple was negative 5, and the vector 2, 1, his scalar multiple output when we multiplied by a matrix was 2. But note that it'll only work on these two guys, but not on every possible column matrix. It only works on certain guys. Okay. And, oh, by the way, let's go back to our A matrix, remembering that our A matrix was 1, 2, 3, negative 4. And recall that the trace is the sum of the main diagonal elements on our square matrix. So if we add up the main diagonal elements, we've got 1 plus negative 4, which is negative 3. The determinant of our matrix is negative 10. Here's something else that's cool. If we add up our eigenvalues, negative 5 plus 2, we get negative 3. And if we multiply our eigenvalues, we get negative 5 times 2, which is negative 10. Ooh, that's cool. So the sum of the eigenvalues will always turn out to be the trace of the original matrix, the sum of the main diagonal elements. And the product of the eigenvalues will always turn out to be the determinant of the matrix. You'll prove that in later math classes. Okay, so let's go ahead and try another one here together. So let's take this B matrix, 0, 1, negative 4, 0, and I want you to find his characteristic equation and eigenvalues, but for right now, not the eigenvectors. Okay, so he's a pretty innocuous, easy-looking kind of guy. So let's do bx equals lambda x, or in other words, b minus lambda I times x equals the 0 vector, which will give me the system, well, 0, 1, negative 4, 0, minus lambda 0, 0, lambda. So that will give me negative lambda, 1, negative 4, and negative lambda. So that's who the b minus lambda I guy is. And if we take that guy, so negative lambda, 1, negative 4, and negative lambda, and we, oops, don't mean the feet here, and we do his determinant, we're going to get lambda squared plus 4. And if we set that determinant equals 0 to get the interesting stuff, we will find our characteristic equation here. But what do you notice about the values of lambda that will make that true? Well, as we've seen before, lambda squared equals -4, so lambda would equal plus or minus 2i. So even though we started off with somebody that was fairly easy, we ended up with complex eigenvalues, and we'll deal with them more later on here in chapter 6. But for right now, just realize that sometimes you can end up with complex eigenvalues. And while we're at it, just one last thing. So we've got 2i and -2i. If I add them up, I get 0, which happens to be the same as 0 plus 0. And our determinant was 4. And if I do 2i times -2i, I get -4i squared, which is also 4, the determinant of the original matrix. So we'll stop there and pick up in the next video.